So we will be also trying to take some questions. So hello, everybody on Zoom. Welcome, and everybody in the room, welcome. First of all, I'd just like to let everyone know, both on Zoom and in the room, that we are doing a live presentation here in the Research Center on Nantucket and also broadcasting on Zoom. So we have a bunch of people out there in Zoom world. Thank you for tuning in. And I will be trying to operate the Zoom at the same time as taking questions and whatnot from folks here in the room. We'll be doing both simultaneously. So I just want to say, hi. I just want to say thank you in advance for your patience and cooperation as we figure out all the tech stuff. But welcome, everybody. My name is Regina Jorgensen. I'm the Director of Astronomy here at Maria Mitchell. And thank you for coming to our final presentations. I should say, by the way, before we start, we call these the final presentations, but they are really not at all final. They are kind of progress reports of where we are right now. But everybody will, all of the interns who you'll see speak today are actually continuing to work on their projects for the next few weeks and sort of finish them up. And everybody will be going to the American Astronomical Society meeting, which will happen in January. And this year it's in Seattle, Washington, and presenting their research in the form of a poster. And so we'll be working on those over the next few months. So this is by no means really final presentations, but it's the last week that the interns are here on Nantucket. And so they'll be presenting kind of what they've been doing up to this point. And so I'd like to just make a couple of acknowledgments before we start. Which is one of them. I'd like to thank, of course, the Maria Mitchell Association for hosting us every summer, and the National Science Foundation, who provides grant funding that supports the NSF-REU. And REU, by the way, stands for Research Experiences for Undergraduates. And we've had NSF support for the last several decades for this program, which has allowed us to invite 6 wonderful interns here every summer from around the country. There is a photo on the screen right now of this year's interns. I'm not going to go through the introductions of everyone because they're all going to introduce themselves right before they speak. But I will just also give a thanks to our affiliated astronomers whose names you can see listed on the screen right now. And these are folks who have also worked with us from around the country this summer and have helped in mentoring the students in their research. So thank you to them. And I think with that, we'll go ahead and start. I'll just also let everybody know the format. So everyone is going to speak for about 8 to 10 minutes or so, and then we'll take a couple questions if there's any questions after each talk. And so for those of you who are on Zoom, please use the Q&A function that you should find somewhere down on the bottom of your screen. And I will try to monitor the questions in the Q&A. And if you're on the Zoom and I don't see your question in time, and for anyone in the room as well, we'll also take another round of questions at the end. So if you didn't get your question in a particular talk and you only think of it later, we'll just do general questions at the end as well. And we'll also try to take any questions from the Zoom. Okay, I think that was all I needed to say. So welcome everyone, and I'm so excited for you all to hear the students' presentations. So with that, I'm going to introduce actually our first speaker, who is Chang from Willamette University. And we're going to have to take a minute to stop screen sharing. No, we don't. You can just go. Yes, sorry.
All right, cool. Thank you, Regina. All right, so hello, everyone. My name is Chang. I am a rising senior at Willamette University, majoring in physics and minoring in archaeology. And this summer, I had the privilege of working with Dr. Natalie Gosnell from Colorado College on modeling the evolution of magnetically active sub-giant stars. So to begin, if you did not know, stars evolve similar to living things. They are born, they live lives, and eventually die. And understanding how a star changes as it progresses through its life is really important in astronomy. And we can understand how a single star evolves by actually looking at a group of stars like you see here. And so immediately, you may realize that the stars are different colors. Some of them are red, some of them are blue, some of them are orangish or yellow. And it turns out that a star's color is actually related to its temperature. And a star's color can give us information about where it is in its life. And so astronomers have come up with a way of organizing stars in a group so we can better understand how a single star evolves. So first, these stars are organized by color, with the blue stars on the left, the red stars on the right, and the stars of intermediate color in the middle. The stars are then ordered by brightness, with the bright stars at the top and the dim stars at the bottom. And the resulting diagram we get actually represents different stages in the star's life, and we can give names to a few of these stages. So this is the same type of diagram, but first I will point out what is called the main sequence. And so the main sequence is where stars will spend the majority of their lives, and it is where our sun currently is in its life. After the main sequence, a star will eventually transition into these subgiant and giant phases, where you'll notice that the size of the dots increases, which represents the size of the star. Now, many stars in our universe can be traced along this diagram. However, there are some stars that are unique and evolve differently. An example of this can be seen in the class of stars known as subgiants. And these are stars that are dimmer than both subgiants and giants, so they are below them on this diagram. And they're also redder or to the right of stars on the main sequence. Now, these stars evolve differently, largely due to what is called a binary system. A binary system is when two stars orbit one another. And in the case of subgiant or sub-subgiants, one star is a subgiant and the other is often a main sequence star. Being in this binary system causes the subgiant star to spin rapidly, which then leads to increased magnetic activity inside the star. This increased magnetic activity then leads to the formation of star spots, which are these black patches that are cooler and darker than the rest of the star. Now, star spots are not unique to subgiants. In fact, our own sun develops star spots as a result of its magnetic activity. Once again, these star spots are these black patches that are cooler and dimmer than the rest of the star. You'll also notice that the amount of star spots on the star can vary. So you could have very few star spots like on the left, or you could have a larger covering of star spots like on the right. And for a size comparison, the size of these star spots can sometimes be about the size of Earth. And so my project was focused on modeling a magnetically active subgiant known as S1063, assuming a 2-temperature surface. And what this means is our current models assume a single temperature surface, or that the star is all one temperature. However, due to the formation of these darker, cooler star spots, we know that these single temperature models will not accurately represent these types of stars. And so we transition to a 2-temperature model where the second temperature accounts for the formation of these star spots. And we're interested in learning how star spots impact our model. And we can find out by comparing our results to actual observations. So what do I mean by comparing our results to actual observations? What I mean is we use data from the space telescope called Gaia. Now, Gaia's whole mission is to look at many, many stars and report back accurate information about those stars, such as how far away the star is or what temperature it is. It does so by looking at a group of stars like you see here, and it views each star individually through 3 different filters: blue, green, and red. What we do is we first build or model our star, which means that we have to assume certain things about the star, such as how big it is.
Can we get rid of this bar?
Press the Q&A. It's probably because it's a Q&A.
Oh, if I press it, it'll go away.
And then you go out, and then it'll go out.
Oh, okay. Sorry. Oh, no. I don't know how to make it go away.
That's good.
But it's still not going away. Sorry, tech issues. We want to make this go away. Can you move it down at least? Because it's blocking the top of your screen. Yeah, okay. There we go.
All right, so what we do is we first build or model our star, which means that we have to assume things about the star, such as how big it is, how many spots are on the star, or what temperature it is, among other things, technology issues. What we then do is we then view our star in the same way that Gaia would, by viewing our star through the same 3 filters that Gaia uses. We then compare how our modeled star looks through these 3 filters to how the actual star looks through the same 3 filters. And if our results match, then great, we've successfully modeled the star. If they don't match, then we go back to our model and we change our assumptions. maybe we made the star too big, or maybe we didn't put enough star spots on the star. And so before I talk about my results, I'd actually like to bring up the results of previous work for context. So previous work has been done on this same star, S1063, and it was concluded that the star would have to be covered by around 30% star spots in order to accurately represent how the star behaves in real life. And so this, I'm gonna move this again. And so this is actually the same type of diagram that I showed at the very beginning of the presentation, where we can trace a star as it transitions between different phases in its life. And so I've labeled the main sequence as I did in the previous plot. And what we see here is basically a previous model called SPOTS. Now SPOTS also is a 2-temperature model, and it also accounts for star spots. However, the methods used in this model are different than the methods that we used. And so the first thing that I'll point out,
I think under more, you can click on hide. If you click more, there should be a hide. Hide floating, yeah.
look at that, perfect. Okay, cool. So the first thing I'll point out is this red square here. And this red square represents the star S1063. And this is S1063 as seen through the Space Telescope Gaia. So this is where S1063 actually is on this diagram. This is essentially our actual observation part. The 3 lines, or the 3 black lines you see, actually represents 3 different runs or versions of this SPOTS model, where the difference between the 3 black lines is how many star spots are on the modeled star. And so initially, you'll see that all 3 of the black lines are pretty close to S1063, which initially would be a good sign. However, the only way that this SPOTS model can come close to modeling S1063 is by assuming that the star is covered by too many spots. Remember earlier I said that previous work on S1063 concluded by saying that S1063 would have to be covered by around 30% star spots, whereas the SPOTS model assumes 51% and 85%, which is too high. What we find this summer with our new model is more accurate. And so this is the same type of plot, however, it's just kind of zoomed in to the black line portion. And again, the red square represents S1063, the star that we are trying to model. And the blue dots represent our modeled star as it progresses through its life. And we can see that our modeled star is close to S1063. And more importantly, our model assumes the correct amount of star spots, which is 30%. And so we conclude that our model is a step in the right direction. And so to summarize, sub-subgiants are found in binary systems and have unique evolutionary paths. This is due to an increase in magnetic activity and the formation of star spots, which are darker and cooler than the rest of the star. In this project, we model a magnetically active sub-subgiant known as S1063, assuming a 2-temperature surface to account for these star spots. And we find that our model is more accurate than previous models. And I'd like to give a big thank you to Dr. Natalie Gosnell and Dr. Regina Jorgensen for all of their lovely support this summer, as well as the rest of the MMA staff for making this summer possible. And last but not least, my fellow astro interns for being such amazing people this whole summer. So yeah, thank you guys.
Awesome. We do have time for questions. Yeah, Celia.
First of all, thank you, Chris. That was such a great talk. I really loved hearing the summation of your project so far. I was wondering what parameter in your model helped get it closer to what how many star spots were predicted to be on the surface of the star?
Yeah, that's a great question. So one of the important things that goes into our model is the relationship between the temperature of the star spots and the temperature of the rest of the star, or the ambient photosphere. And so, for example, the SPOTS model assumes that there is a constant ratio between the two, whereas we try a few different methods, including the constant ratio method, as well as a few other ways of relating the 2 temperatures. But yeah, the relation of the temperatures is a major part of this model.
Cool. Thank you.
Yeah.
How do the star spots form on other stars that isn't the one orbiting around the other one?
Yeah, that's a good question. So
really quickly repeat the question for the Zoom.
Oh,
Sorry
okay,
for interrupting you.
Yeah. So the question was, how do star spots form on other stars that aren't rotating or that aren't in binary systems? Yeah, so it's a good question. So star spots form in general due to just high magnetic activity. So it's anything that could cause an increase in magnetic activity, and increased spinning just happens to be one of those things. But any star that just has a high amount of magnetic activity definitely has a chance of developing these star spots.
And can you apply like the model that you used on this star on other stars now?
So I think the main point, oh, sorry. So the question was, can we use this model to model other stars as well? I think the main point of this model is that these stars evolve differently than other stars that we can already model.
Yeah.
And so I think by having an accurate model that represents these unique stars, we can then kind of ask questions about maybe how these stars interact with other objects in space and whatnot. So yeah.
Okay, I don't see any other questions. If there are questions on Zoom, feel free to put them in the Q&A and we will definitely get to them at the end. With that, let's thank Chris again. Let's get rid of that top bar.
Do more? No, just do more and let's get rid of it. Yeah, there we go. Can we get rid of that too? I don't know, maybe not. Okay, yeah, okay, that's good because it was blocking.
Regina,
Yes,
just a heads up that the light that is on above the speaker's head has kind of a glare on Zoom.
okay, I think I've lowered it.
Perfect, that's perfect.
Hi, everyone. I'm Baslani. I'm a current junior at the University of Connecticut. And for this summer, I've been working with Dr. Shazri Mohammed and Dr. Rodolfo Montez, simulating exploding stars. And so to start off, I just want to give you guys some background information. So like Chris said earlier, stars don't kind of exist in space. They're actually born and they have life stages and then they die. And this life cycle of a mass actually depends on how big it is when it's first formed. And so a low mass star is a star that is 8 times bigger than our sun or lower than that. And so all stars are born out of what we call a nebula. And a nebula is basically just a cloud of gas and dust. And when there is enough gas and dust in a particular area, sometimes gravity can collapse this and form a star. And so this is what we call a main sequence star. And what a star does, how it fuels itself, is it takes helium and it takes hydrogen and it turns it into helium. And when the hydrogen runs out, the layers of the star will start to expand and become cooler. And because of this, it will turn red in color. And so this is its next stage, and it's called a red giant. And after the hydrogen is all used up, the star will start using the helium to convert it into carbon. And when all the helium is kind of used up, the core of the star will start to shrink and it will become what we call a white dwarf. And a white dwarf is basically a dead star, and it's about the size of our Earth. And then the outer layers of this red giant will become another nebula. And so this image is not to scale, but if I did scale it, it looks something like this. Yeah. And so what I'm primarily interested in this summer is about the white dwarf. What happens to a white dwarf afterwards? Does it die? Does it just kind of stay there? And so for some more background information, Chris also mentioned this, binary systems, and basically these systems are when 2 stars are orbiting around each other. And if one of these stars is a white dwarf, you get something really cool that starts happening, an explosion. And so what you see here is its companion star will actually start giving off some of its mass to the white dwarf. And you can see around the white dwarf, there is some sort of disk, and this is called an accretion disk. So the mass will kind of fall off into this disk and start spinning around the star. And then what will happen is that after that, it will the gas from the red giant will start to kind of form an envelope around the white dwarf. And at some point when there's enough pressure in this outer envelope, the envelope will explode into a nova explosion. And I just want to make a distinction really quick that this is a nova and not a supernova. And a supernova, basically when that happens, the star will kind of become destroyed. But when a nova happens, the star will still be there afterwards. And so what you end up getting is kind of this cycle of the companion star giving its mass to the white dwarf, and then the white dwarf, the layer on top of it will start exploding. So you get like a big cycle of just recurrent novas. This is what we call them. And so for this summer, I've been working on an object called RS-Ophiuchi, and it's a binary star system that consists of a white dwarf and a red giant star. And so this image over here is just an image of the night sky. And this cloudy thing kind of in the middle that's sort of arcing is the Milky Way. And so if you can look kind of to the bottom right of it and kind of go up, you'll find the constellation of Fucus. And to the left of this, you'll see RS-Ophiuchi. So you can see this in our own night sky. If you go outside tonight, you can locate the star. And so when looking at RS-Ophiuchi, I've been looking at two different kind of point of views of looking at it. And the first way to look at it is a face-on view. And so you have like a disc right here, and you can think of this as being kind of a bird and just flying above. So you're looking down on it. And so here you have your white dwarf and a red giant. And then you have like this outer disk, but it's not the accretion disk. It's a different type of disk, and we call it the circumstellar disk. And the second way to look at it is called an edge-on view. And this is, so first we were looking as like kind of a bird, but now we're kind of even with it. So we're looking at it from its side. And so you have your white dwarf, your red giant, and the accretion disk I was talking about before. And now this is the circumstellar disk. And so when a nova happens, there are two different things that can happen. So for the face-on view, the gas will kind of just hit the, kind of push the gas from the circumstellar disk out. And so these blue arrows just kind of show like the gas from the explosion, and it will just push the gas out gradually. But on the edge-on view, there's nothing on the top or on the bottom to kind of contain the explosion. So what ends up happening is that the gas from the nova will hit the red giant, and it will hit the sides of the circumstellar disk and kind of go up and down. And so here's the disk. The gas will flow out like this. What you get is this two lobe type features on the top and bottom. And so for this summer, I've been looking at the face-on view and the edge-on view, and kind of see like where the gas goes and how it affects the gas outside of like the circumstellar disk. And so I use a simulation to model what would happen during a first nova and then a second nova as well. And so these next videos will show you the nova explosions for the first nova. So this is the face-on view I was talking about before. And so you can see the gas from the nova actually will push out all of the other gas that already exists there. And for the edge-on view, you can see that what you get is these two really big lobes on the top and bottom. And what's in the middle is actually the circumstellar disk that I was talking about before. And so it appears to be shrinking, but that's only because it's kind of staying the same size. And we're actually zooming out of this picture because the top and the bottom lobes are just getting very, very large. And so that's why these axes are changing on the top and the bottom. And so my next slide will be for the second nova. And so we're looking at the density, and density is just basically the amount of stuff in a particular area. And so I ran simulations for 3 different types of explosion velocities. And here are the corresponding plots for each of them. And so a couple things that I will point out is just the size of these lobes and of the hourglass. So the lower velocity is, the nova is actually smaller, the hourglass figure is smaller, and then it gets kind of bigger the higher your explosion velocity is. And another thing you might note is for the lower explosion velocity, you have a higher density than the high explosion velocity. And this is just because if the particles are going faster, they can push everything else out further away. So you're having less particles in the same amount of area or volume. And another thing I will point out is you can kind of see an inner hourglass shape. And so that's everything from the second nova, and everything that's kind of like a little above and below is from the first nova. And so what happens is that it's just pushing out the gas even more. And so why is this research important? So to make simulations, we use physics that we already know. And we want to see if these are actually accurate. So we want to observe them to what we want to use observations and see if our simulations are accurate. And so if they're not accurate, we will go back and change some of the physics that we have made. And so for my next step for this project is to actually use, this is a picture of Chandra X-ray telescope. And so I will use X-rays to kind of compare and see if my simulations are accurate or not. And another reason why this research is important is because it has greater implications for astronomy. So a lot of astronomers think that this type of system with like a white dwarf and another star will eventually lead to a supernova. And at this point, when the star goes supernova, it will destroy the white dwarf. And we can use the brightness of that supernova to measure distances to like faraway galaxies. And so as a summary, many stars are in binary systems. And if one of them is a white dwarf, you can have a recurrent nova. And we want to simulate these models to understand what we see in telescope observations. And astronomers think that eventually these stars will go supernova, and when they do, we can use their brightness to study faraway galaxies. And yeah.
Any question? If we have any questions on the Zoom, go ahead and put them in. Yeah, Johanna.
How frequently does this occur?
Okay, so for
I'll just repeat the question really quickly. The question was, how frequently does this occur? Just for the people on Zoom, sorry.
So for my star, it occurs about every 20 years. There is a star that explodes every year. And so depending on how big the white dwarf already is, it kind of dictates how often they explode.
Great, thank you. Thank you so much, that was awesome. I really loved your plots. The simulation just produced some really beautiful images. I was wondering if you could, like, do we expect to see different densities over like different novae? So like the first one might have a higher density and it will get lower density as it goes on, or vice versa?
So every time in the simulations, every time we inject another nova, we're actually adding mass.
Okay.
So there will be more particles,
Okay.
but I think for the more nova we have, the further out all the gas particles would be pushed away. So I think the center will always have like the highest density, but then as depending on like which velocity we use, the lobes will always have less density.
Okay, cool. Thank you.
How long does it take for these explosions to occur? Because I don't know if the GIF was accurate, if it's kind of like happening, or if it takes like a long time.
So the question was, how long did the explosions take?
So the explosions take a very short amount of time, like maybe 1 second, 2 seconds, maybe less than that.
I thought that was a sped up version.
Yeah, it's a slowed down version. Yeah, in our actual simulations, we like model it for 20 years. Yeah.
So like, this is gonna sound so dumb, but how do you like, does the telescope that you were referencing? Like, is that what you use to see the like explosions, or how do you see them?
So the simulation that I used, we actually use.
Put it back on the screen. Go ahead.
Yeah, we actually use like computers to do this, and through like code, we will write like physics equations to kind of model what is happening. We can make mock X-ray observations doing more computer science, and then the telescope will actually it will kind of just show us these X-rays. And so after we've made the mock X-rays, we can go and compare if our X-rays match the X-rays that come out of the telescope.
There is a question on the Zoom, which is from Kara, who says, great talk, Danya. Curious where the X-rays you will observe with Chandra come from. How are they produced and how closely do they trace the density you show in your awesome simulations? And you might have just sort of answered that in talking about where the X-rays come from.
So the X-rays, we expect the X-rays to come from areas that are the most dense and the hottest. So that would be sort of in the center. And then also the low parts, like the very top parts and the bottom parts as well. So that's where we expect to find them. And Rudolph Montes, he actually has these observations. So once I will make my mock X-ray emission, then we can go back to his paper and kind of compare.
Awesome. Okay, thank you so much, Dr. Okay, next up we have Deb, who will introduce herself.
Yeah, so hi everyone, my name is Devashree Falapaneni, and I'm a rising junior attending Cornell University. And this summer I've been working with Dr. Leah Corrales from the University of Michigan on exploring interstellar dust. And so when we think about the space between stars, you might picture pitch black and think it's super empty, but in fact it's not. It's full of something we call the interstellar medium, and just about 1% of the total mass of the interstellar medium is made up of dust grains. And these dust grains are usually made up of carbon or silica to begin with, but later accumulate other atoms like nitrogen, oxygen, carbon, or hydrogen. And they're really tiny in size too. They range from just about a few atoms put together to a few microns in size. So the largest dust grain you'll find is so much smaller than the smallest sand grain you could find here on Nantucket. So they're really tiny. And in this image, I'm showing an edge-on galaxy, so a galaxy on its side, against a background of stars and other bright objects. And you see dust in this picture, not only in the pitch black regions I was describing, but also within this galaxy. This really dark stripe spanning the galaxy is actually dust. It's blocking light from us, and so that's why we see this really dark patch. And so dust seems to be almost everywhere in this picture, and that's because it's literally everywhere in the universe. And so that's a really important reason to study dust, of course, but dust also really affects what we see. And so in this picture of the pillars of creation, you see that in the visible light, you see really thick plumes of gas and dust, especially in those darker regions. But if you turn to infrared, which is a longer wavelength, and it allows you to probe past the dust essentially, and allows you to see the background of bright stars and other objects. And so that's why you see all the stars and other really bright objects from that were hiding before. And so that can be an important reason to study dust as well, because dust affects different wavelengths in different ways, and that's interesting to astronomers. And dust is also really vital to lots of different astronomical processes. In fact, it's really important to star formation. Dust itself is formed when stars die, and this releases, so when stars die, gas and dust is released through the fact that the outer layers of the star sort of expand and release this. And stars also fuse different atoms to create elements, and that process also releases dust into the interstellar medium. But just in the way that these dust grains are formed by stars, dust grains also help in terms of forming stars. And this is because in star forming regions, hydrogen atoms are moving super fast. And this means that when they collide, they won't actually stick together to form molecular hydrogen, which is a key component to star formation. But because there's dust grains, and these dust grains can have a slightly sticky surface, the hydrogen atoms can actually attach to these dust grains, which then allows for the formation of molecular hydrogen and then eventually form stars. So dust is really helpful in terms of creating all the stars that we see today. And so since dust is super important and it affects different wavelengths in different ways, astronomers use lots of different wavelengths of light to study dust. But this summer, I've been focusing on using X-rays as a key way to understand more about dust. And so X-rays can be really helpful because they're really sensitive to the size distribution of the dust grains that we're studying and really help place a limit on what the largest dust grain you could find potentially is. And they're also really helpful because they allow us to probe farther into the universe in terms of dust than other wavelengths. And so I've been using data from the NASA Chandra X-ray Observatory as a way to study dust. And you might wonder, even using Chandra, which is the best X-ray telescope out there in space right now, how would I study dust? Well, it's through a phenomenon called dust scattering. And this happens when there's a Chandra or an X-ray telescope looking at a really bright X-ray source. And this X-ray source is just emitting lots of X-rays. And so the most direct path for these X-rays to reach back to the telescope is just a straight line. But if there's a dust cloud, the light coming from the X-ray source will hit dust grains and the path of the light will be altered, causing us to see what's called a dust scattering ring. And the closer this dust cloud is to the X-ray source, the smaller the ring that we see. And so this is exactly what we see in observation as well. This is a picture of a neutron star, which is an X-ray source in this case, and forming these dust scattering rings. You might see this dark stripe spanning the observation. That's just where the telescope doesn't collect any light, so feel free to ignore that. But you see lots of these ring structures forming. And this ring structure actually only forms when you have really bright X-ray sources that flare up, meaning that they're really bright for short periods of time and then really dim for longer periods of time. But that's not super common for us to catch in the universe using telescopes. And what's more common is that we have a really bright X-ray source that's just super bright for long periods of time. And so when that happens, you see a more diffuse looking observation, like what you see here on the right. And these type of observations are called X-ray halos. And that's the kind of observation I've been studying. I've been studying a source called GX13+1, which is exactly what you see here. And I have Chandra data that has looked at this source. And this data tells me about, one, the number of photons that have hit at any particular point on the telescope, or pixel in this image, for example, and also the energy of each photon that's hit the telescope. And so in this image, all the little dots, the gray dots that you're seeing, are actually the photons. And in this image, the information that I have are what the photon are light from both dust scattering that I was describing, but also light that's just coming directly from the source itself. But personally, I'm really interested in studying dust and its properties, so I don't want light that's coming from the source at all. So I build what's called a point spread function to remove the effects of the source light in general. So in astronomy, and a lot of the objects that we're looking at are super far away. And so this means that to us or to a telescope, they're essentially point sources. And so when a telescope looks at a point source, it should just see a point, like what's on the left. But what it actually sees is a little bit different. It's more like what's on the right, something more distorted because of the telescope's mirrors or other instrumental effects. And so we need to also model what a point source looks like to the telescope in considering like removing what a point source, the point source that we're using. And so since we can't disentangle like what the dust scattering is versus what light from the source is from our initial image, we turn to what's called a calibration source to model this source light. And the calibration source that I'm using is essentially just a really bright X-ray source that has no dust scattering at all. So it's literally just a bright X-ray point source. And so to model what the point source looks like, I essentially count up the number of photons in each little circle that I'm drawing from the source center. And then so on, all the way out to the end. So I'm counting in the second circle, I'm counting the light between the second and the first, and so on all the way out. And so I'll expect the brightest points to be sort of closer to the center. And as we go farther out, they'll be dimmer. And so I'm modeling how the brightness essentially falls off as we go farther from the source. And so this is exactly the sort of plot that I've been building. And so on the x-axis, you'll see that I'm going farther away from the source. And on the y-axis, you're seeing brightness or the number of photons. And the spacing of each point is just the spacing between two different rings that I've drawn previously. And so you see exactly what I was saying, where closer to the source, it's really bright, source center. And as it goes farther out, it's sort of falling off. And this is the type of model we want to build. And so I've essentially fit a model to this to make sure that I'm not accounting for any random noise or instrumental effects that are specific to this other source that I've used as the calibration source, but are not relevant for my source particularly, which is GX13+1. And so this model that I've built is exactly the point spread function that I'll need. So to just reiterate, the photons that I was seeing in this were both from dust scattering in the source. But now that I have a point spread function, I can remove the contribution of light that's coming from the source so that I can study just the dust scattering. And this is exactly what I'll be doing in the future. I'll be able to fit different dust models to understand more about the properties and composition of dust between the telescope Chandra and this really bright X-ray source, GX13+1. And so the main things that I want you to take away are that, one, that dust is super vital to lots of different astronomical processes, and that we can use X-rays as a way to study and understand different things about dust. And that these rings and halos are really just an effect of light being scattered by these dust particles, and that they tell us a lot about the actual properties of the dust between the telescope and this really bright X-ray source we're considering. And so thank you so much, and thank you to, of course, my AA.
Any questions?
Thank you, Deb. That was awesome. I was wondering, when you see like the rings in this type of observation, and with the diagram you're showing that dust clouds that are closer to the X-ray source will produce smaller rings. So can we count how many dust clouds that source's light has passed through by how many rings?
Yeah, actually, exactly. So in these observations, like especially the ones that have rings, actually, the funny thing is that the ones that have rings are really rare for us to catch because they're really bright outbursts. And this means that the telescope has to manage to move to that source and catch it in time before these outbursts last for weeks. So not enough time sometimes for the telescope to catch it. So when it does, we do get this really pretty looking plots, but and they tell us a lot. So yeah, exactly. So the number of rings tells us more about the number of dust clouds, but also these rings are sort of an effect as well of just the source being bright and dim at the same time. So what's actually happening is when the light gets scattered, it sort of has a longer path, right? So that light that's been scattered is from an older time by the time it hits so the outer regions will essentially be the brighter regions because they're taken longer to travel essentially before. So that's why we see this sort of ring structure as well. But yeah, we can definitely also tell about how many dust clouds and things, but that's more why the ring structure forms because of this
Cool, thank you.
And we have a related question on the Zoom, which is, what do the colors mean in your pictures of the dust scattering rings? I think the other one.
Yeah, I'm gonna go all the way. I have just a slide with the two.
Awesome.
So in here, the colors are actually, so one thing I'll point out first is that this looks a bit different from this, and I think we all agree on that because this is a little bit smoothed out. The photons are actually more like this because they're little points and dots when they hit the detector, but this has been smoothed out, so you see more like diffuse looking thing. But the colors themselves, the reds are more low energy, and the blues are just high energy, and a lot of the yellow greens are somewhere in the middle, so the colors just represent different energies. Yeah.
So the point spread function you made, can it be applied to any point source observed with this telescope?
Yeah, so that's a really good question. And what happens is that when we build this point spread function, it's exactly right that we could use it for other sources as well when we're looking at observations. Essentially, we're just modeling how the telescope views a point source. So it's not specific to like using GX13+1 because the constraints or like the conditions for having the point source were one, that there's no dust or minimal effects from dust, and that it's something just really bright. So if we were to do any other dust scattering source studies, the only consideration would be that, so my observation of GX13+1 used a very specific part of the like telescope to do it. So not the entire available sort of thing. And so that's one thing we had to consider when building, like choosing what source to use. And so if we had a different type of observation, it would be tricky to reuse our own source. But if we had something that used the same instrument on the telescope, yes, we could totally use this as a way to do that as well. Yeah.
What is the source? Is it a star?
Yeah, no, so, okay, so let me move this way. So X-ray sources are really interesting. They can be a range of different things. They can be like active galactic nuclei, which are like kind of black hole stuff. And then they can be supernova remnants. Danya talked a little bit about supernova. And then they can be like X-ray binaries where where there's one is a star and the other is like a black hole or a neutron star. So in the case of the two that I was describing, so this one has a neutron star and a supernova remnant around it. And then this one is a black hole and a star. So, and then my source was a neutron star and a star itself. So they're very interesting in their composition. Cool.
All right. Well, thank you again. Thank you.
All right. Hello, everyone. My name is Untitled, and I'm a rising junior at Yale University studying astrophysics. And this summer, my research has been on searching for recoiling black holes. So first off, what really is a black hole? A black hole is when you have so much stuff in such a tiny location that it just collapses in on itself. And its gravity is so strong that it sucks in anything that comes too close. So whether that's dust, gas, or even a star, everything will get pulled in. Actually, not even light can escape a black hole, which is why it's called a black hole, because we can't see the light from it. But while we can't directly see a black hole itself, we can sometimes see the light from stuff around it. So when a black hole is super hungry and is eating a lot of stuff, some of that will get pulled into a disk around the black hole called an accretion disk. And when there's a lot of stuff in that disk and it's moving really fast, that disk will get hot and it'll start to glow. So when we see that glow, we know that, oh, there's probably a black hole there. So most galaxies out there in our universe have a supermassive black hole at their centers. So a supermassive black hole is millions to billions of times the mass of our sun. So they're really, really big. And they're really important because galaxies and black holes really evolve together. So you've heard this analogy before today, but just like people, galaxies are born, they grow bigger and they change over time, and then they'll eventually die. And black holes really make that journey together with their galaxy. They'll affect their galaxy and the galaxy will affect the black hole back. So you can't really study one without studying the other. But you'll notice that I said most galaxies are home to supermassive black holes. What about the ones that don't? What happened there? So actually out there in our universe, galaxies aren't standing still. They're moving around and they can even crash into each other and form a new, even bigger galaxy. And if these galaxies had supermassive black holes in their centers, then when the galaxies collide, the black holes will also collide to form a bigger black hole. So this next slide shows an animation of these two black holes with their accretion disks. They're circling around each other and they eventually merge into one new giant black hole. And sometimes really weird things can happen during this process. And if the conditions are just right, this new large black hole will get kicked out of the center of its galaxy. If the kick is strong enough, it'll completely launch it out of its galaxy. But if it's weaker, it'll still stay in the galaxy, but not be in the center. So these are called recoiling black holes. And this summer, I've been trying to create a method to find the recoiling black holes. So that's kind of hard though. There are billions and billions of galaxies out there to search. And if I had to go out and take a picture of each one, study it and be like, oh, no recoiling black hole, then it would probably take me forever. So thankfully in astronomy, we have these things called telescope surveys. So these are telescopes where their main job is to just go out and take pictures of the entire sky multiple times. And then they make that data publicly available so that people like me can use it for our research. The specific survey that I'll be using in the future is from the Vera Reuben Observatory. So this is a super cool telescope that's currently being built on a mountain in Chile. And this specific one is awesome because it'll take a picture of the entire visible sky from this location every 3 days. So we're gonna get a ton of data from this. And its resolution is so good that you could see a golf ball from 15 miles away with this. So that's like one end of Nantucket to the other. So while we're waiting for this telescope to be built, I've been using existing data from a different survey. That survey didn't take photos as often, and the telescope was smaller, so it can't look as far into space. But the idea is that if we can find recoiling black holes with the existing data, then we can definitely do it with the much better data from Vera Reuben in the future. So what is this method? How do we find recoiling black holes? So let's say you've got your galaxy and its black hole gets kicked out of the center onto the side. The interesting thing about black holes is that their accretion disks aren't actually at a constant brightness. They'll flicker over time, depending on how much stuff the black hole is eating. If it's eating a lot, the disk will glow brightly, and if it's not eating so much, it'll be a little dimmer. And so it'll flicker over the course of hours to days. So when a telescope sees something like this in the sky, it sees a galaxy that isn't changing in brightness and then a flickering source. And when a telescope looks at an object, it tries to calculate where the center of it is, what's its coordinates. But because there's two different bright sources here, the telescope gets confused trying to calculate that. When the black hole is super bright, the telescope thinks, oh, that's where the center is. So it'll think the center is closer to the black hole. When the accretion disk is dimmer, it thinks, oh, the bright center of the galaxy is actually where the coordinates are. So it'll be closer to that. And as the telescope takes multiple pictures of the system over time, months to years, it'll keep calculating centers and they'll be all over the place because the telescope's getting so confused. So when we see this jitter, we know that, oh, it looks like that there's a galaxy with a point source out there that's flickering. So it could be a recoiling black hole. But looking at this, you might be kind of confused. Why is the telescope having such a hard time if I can very clearly see the bright center of the galaxy and the bright black hole? But this picture is actually a galaxy that's pretty close to us, so we can see a lot of detail. But most of the galaxies that I'm looking at are super far away and they look pretty small. You can kind of think of it as a good analogy is if you're driving on the road at night and there's a really annoying car coming towards you with its high beam headlights on. In the distance, it kind of just looks like this big blinding blob of light. And it's not until the car comes closer that you can actually see that it has two individual headlights. So that's basically what's going on with this galaxy. With these galaxies, they're so far away that they're just blobs. And the cool thing is, we looked at our existing data and we saw this jitter. So these are two different galaxies. And each of these red points are where the telescope has calculated the center of the object to be. And on the left is basically our control galaxy. It's a galaxy that has a black hole in the center. So since both the bright black hole and the bright center of the galaxy are in the same place, The telescope doesn't get confused. It knows exactly where the center is. So there's very little jitter there. But when we have a galaxy with a recoiling black hole, the telescope is getting super confused and there's lots of jitter there. And actually, the really cool thing is we were able to use this method just last week to find a brand new recoiling black hole candidate. That's this fuzzy galaxy all the way out there in the universe. So this bright spot is what we think the recoiling black hole is. And it's definitely shifted from where we think the center of the galaxy is. So that was super, super cool. And hopefully we'll find even more using this method. So as a quick recap, most galaxies have supermassive black holes in their centers. When galaxies collide, the new formed black hole can get kicked out of the center of the galaxy. We can find these recoiling black holes by seeing their coordinate jitter in telescope data. And finding recoiling black holes will help us learn more about how galaxies and black holes evolve together. So thank you so much, and I'd be happy to take any questions.
Okay, do we have any questions?
Celia.
I'm your biggest fans. That's all I wanted, but thank you. That was really wonderful. I'm a huge fan of black holes and AGN. And I was just wondering, one, what was the wavelength of light you were using this summer? And considering that black holes emit at all wavelengths of light, specifically when they're accreting material, would there be another kind of instrument that looks in a different type of light that you'd be kind of interested in using to identify these types of systems?
Yeah, okay, I'm gonna go back a couple slides. So these images, these were in visible light. So I think the background image here is like I band, which is like, I think that's green. But there were different colors that we looked at when looking at the black hole in specific, since the disk is usually bluer than its surrounding galaxy, which usually looks redder. So we did see more jitter in the bluer observations than the redder observations. And also one of the follow-up things that we're doing now that we have, like, we actually have a second candidate that we found yesterday too. And we're trying to look at them in radio wavelengths, since black holes will also sometimes be radio loud if they have jets pointed towards us. So yeah, lots of more data to look at.
Wow, a hot off the presses result. Just announced to you all. Celia has a second. Yeah.
Okay. It's just so quick. Would you consider doing kind of like profiles of the galaxy to kind of see how I'm gonna use a jargon term, sorry, but like a light weighted ratio, so how much like light is like being contributed from the system, and seeing how that could change over time too, to like figure out, you know, if more light is coming from one place, like over another time skewing, you know, the measure of like stars' ages or like other things.
That's a great question. I haven't thought about that as much. I think mostly we've been looking at the contours of like where the brightness is different. So you can see like when you have like the extended galaxy in the AGN, there's like lots of contours over here, and it kind of like is getting pulled by the galaxy out there. But yeah, I know that there was one paper that I was reading that was like, oh, like when you have an ejected black hole, you can sometimes see like enhanced like H alpha, so a different wavelength as it in its trail as it came from the center of the galaxy. So there's a lot of cool stuff to look at. Yeah.
See if we have any questions on the Zoom. We don't, so go ahead, Jacob.
So if a black hole is not in the center, is it necessarily ejected? Can it form not in the center?
Yeah, so you can have other black holes that aren't like the supermassive black hole. So there are actually, a fact that I learned today, there's like 100 million like stellar mass black holes out there in our galaxy. But the one in the center is the one that's like millions and billions of times the mass of our sun. And that can only really form in the center because that's where all like the mass is coming towards the center. So if we see it out to the side, it's probably came from the center.
Good question. Okay. Awesome. I don't think there's any other questions on Zoom. So thank you.
Right.
I think our next speaker is actually joining us from Zoom. So I am going to, let me see, try to stop screen sharing here. Of course, I made the bar go away and okay. Oh, perfect. Okay, that worked.
Can you see me and can you hear me?
Give us 1 second, Will. Let me
Alrighty.
There we go. Okay, we can see you in the room, and I believe that we can also see you on the Zoom.
Are you in outer space? Right?
Yes. So we are
Awesome.
good to go, Will.
And you can hear me all right?
We can hear you, yes.
Fabulous. Alrighty. Good evening. My name is Will Jarvis. I'm a rising senior at the University of Wisconsin-Madison. This summer, I have been privileged to work with Dr. Regina Jorgensen studying a type of galaxy called a damped Lyman alpha system. When we look through the universe, we're really looking through time, looking into the past. Because light travels at a finite speed, it takes time for it to reach us. Some of that light has been traveling for billions of years, showing how the universe has appeared at different times. Early in the universe, galaxies were small, 1/100th to 1/10 of the mass of the Milky Way, our galaxy. As time progressed, galaxies merged and stars formed, growing some of these galaxies, building some of them into the spectacular spiral galaxies that we see in the modern universe, like our own Milky Way. But what led to this evolution? Typically, to answer that, we would take a picture of the galaxies, like those shown on screen, and we would study characteristics about them, like their density, their brightness, how quickly they form stars. But these bias us to only the bright galaxies, the ones that we're able to visually see. We're missing all of the dim ones. Luckily, possible proto-Milky Way galaxies called damped Lyman alpha or DLA systems may help us understand this evolution. DLAs are exciting because we don't need to visually see them in order to study them. They absorb light from other objects, and from that we can learn about the galaxies themselves. We search for DLAs by looking at objects known as quasars, named for being quasi-stellar objects that look like stars but in fact aren't. They are supermassive black holes and incredibly far away galaxies, devouring matter, which makes them very, very bright. DLAs appear to block or absorb some of that light from reaching us. This figure shows a very simplified view of a DLA, with a galaxy, the DLA, between Earth and a quasar. That DLA would be blocking the quasar's light. To understand DLAs, we need to take a look at the spectrum of the quasar. We split up the light into all of its constituent colors, like using a prism, allowing us to identify specific elements from the quasar. These appear as tall peaks called emission lines, where electrons in the gas are excited and emit light at a particular wavelength. Here is an example of both an emission and an absorption line for the element of hydrogen. It is these lines that allow us to study the composition and evolutionary history of the DLAs. Here, we show the basic principles of what we're looking for. On the left, a quasar emits light, creating some emission. As we will see later, there are many emission lines present. However, here, we're just showing a general broad curve representing the quasar's entire spectrum. Now, on the right, we show that same quasar, except now with a DLA galaxy in front of it. The gas inside that galaxy is absorbing the light at a particular wavelength, specifically that of the Lyman alpha transition of neutral hydrogen. It creates a trough in the spectrum of the quasar. That's that kind of winged shape on the bottom right. By studying these absorption features, we can find DLAs. However, we still have kind of a big problem. While absorption tells us a lot about the galaxy, we need emission to understand more about the galaxy's size, its star formation processes, and evolutionary history. That emission is hard to come by in the case of DLAs. Quasars are incredibly bright, being sometimes trillions of times brighter than the sun. This means that DLAs are often overshone by the bright quasars behind them. But that does not mean it is impossible. A 2004 study detected emission from a DLA using a novel technique. This image you can think of as like a negative of a picture. This is the Quasars Spectrum focused around the DLA, except where the black regions represent emission and the lighter regions where there's no emission. The DLA trough here is actually where that thick line on the outsides break. That little dot in the center is in fact actually coming from the DLA itself. That is Lyman alpha emission from the DLA galaxy that has been detected here. However, to truly understand these galaxies, we need to find many more of them so that we may clarify how they behave and evolve. You can't just look at one, you need an entire population. So that brings us to our work. We began with a sample of 9 DLAs observed with the Keck-2 telescope in Hawaii. This telescope has a mirror that is 10 meters in diameter, which is larger than the research center that you are sitting in now. Each DLA received between 45 minutes and 3 hours of observation time, averaging out to about an hour. Attached to Keck is a special instrument called an integral field spectrograph, the Keck Cosmic Web Imager, which functioned as our camera. Using this instrument, we were able to detect objects so faint, it would be like detecting a 50-watt light bulb on Mars. The spectrograph works by splitting up the light into different slices, allowing you to create a normal-looking image, but getting a spectrum at every single pixel in the picture, creating what's called a data cube. This allows us to get both high-resolution pictures of the target and high-resolution spectra of that same target. In the figure here, you can see a cartoon image of a galaxy. At every X and Y position on that image, we also get a spectrum of that part of the galaxy, as indicated by the smaller box in the top left showing a spectrum from 1 pixel. This powerful technique enables us to study galaxies with unprecedented detail. This summer, I calibrated and reduced the data into cubes for 3 observations using a software called Pipette. This software takes in the raw spectra off of the telescope and turns them into images like the one you can see at right. This is an extremely difficult process, taking me about 9 weeks to reduce the data for just 3 galaxies, and we are still working to improve this process. At the right, that image that I mentioned before is a picture of the quasar BO551-336 collapsed across all wavelengths. Next, you can see my full spectrum for that same galaxy summed over that bright quasar in the middle. It shows many absorption and emission lines associated with the quasar. That big line that you see in the middle, for example, right here, is actually the quasar's hydrogen emission. Hidden on the left side of this figure, however, is the DLA and the DLA trough. It's highlighted in red down in the bottom left. However, our most exciting result is not about BO551, but rather the promising detection of a Lyman alpha emission line in the source J1305 plus 0924. Using the line's wavelength, we were able to calculate the distance to it of about 10.4 billion light years away. Future work will investigate that emission line highlighted on the right in order to calculate the star formation rate and mass of the DLA galaxy. So this summer, we searched for damped Lyman alpha systems in emission using the Keck telescope in Hawaii. These galaxies are extremely faint since they are detected by the light they absorb, not by what they emit, allowing us to observe more than just the brightest galaxies. Using these observations, we're able to find 1 positive detection of a Lyman alpha emission line in a DLA thus far, though we continue the long process of data reduction. Ultimately, when we have collected a large enough sample of these galaxies, we'll be able to analyze them to understand more about how they evolved into the galaxies of today. If you have any questions about my work, please feel free to email me at the listed address. I'd like to thank everyone at the MMA for a wonderful summer, but most specifically my wonderful friends, the Astro interns, my family, and Dr. Regina Jorgensen, who is a terrific help and a fantastic mentor this summer. I'll now take any questions that you may have.
Awesome job. Thank you, Will. Let's see if we have any. I don't see any. If anybody has any questions in Zoom world, feel free to put them in the Q&A. And we have a question from Celia in the room. I will restate the question in case you can't hear it.
Thank you, Will. That was really awesome. And I can attest to your hard work on that pipette reduction. I'm really interested with the emission. What was your kind of process to determining that was real emission rather than a spurious detection?
That is a great question. So here, let me go back. So the main thing we did, so what we would like to do in the long term is to basically look at the noise level across the image and use that to basically set a threshold above which anything that's detected above that threshold would have to be an emission line, pretty much. That's the end goal. However, because we're still working with pipette and things are difficult, the noise values are still not quite up to snuff. So what we did instead was we basically looked at the root mean squared of the trough of the DLA. So basically, you can think of that as basically looking at all of the emission inside that trough, and then looking at how much that varies over the trough. You can work out a measure of that called the root mean square, and we plotted that as this red line right here. As you can see, the emission line just peaks above that red line there, and because of that, we're pretty sure that this is actually DLA emission.
Good question. Are there any other questions? Or if anybody has any questions in Zoom, please pop them in the Q&A. We have one more question in the room from Joanna. I'll repeat it.
Well, why did you choose this topic?
Did you hear that, Will?
I did not.
Okay, Joanna's wondering why you chose this topic.
Oh, okay. So I think a lot of this goes back to, well, there's two reasons. The first one is that I really wanted some experience working on data reduction. Data reduction is an incredibly important process for being an observational astronomer. I don't work with simulations where I design all of the parameters myself. I'm out taking data of the universe. And learning how to reduce that data to make it usable and how to analyze that is an incredibly important skill. It's also really difficult, as is evident by the fact that we were only able to actually reduce 3 galaxies in an entire summer. This is a process that can take 6 months to a year or more, very, very commonly. The other reason is this is just a cool topic because these DLAs, well, one of the things that we are curious about is basically how they're forming stars, because there's a lot of questions about how the universe has formed stars at different points in its age. Because, you know, going back to the very beginning of this talk where I mentioned these galaxies up at the top right here are small. They're at most about 1/10 of the mass of the Milky Way. And they're dim and their morphologies are weird. So they don't really look like big galaxies like we see today. By studying DLAs, we can basically try to figure out how these galaxies in the top right formed enough stars and got big enough to turn into these big spiral galaxies that we're seeing in the bottom left. So by studying these, we get to, you know, kind of indirectly learn a little bit about how the Milky Way itself may have turned into the Milky Way that we know and love today.
Thanks, Will.
Thank you, Will. And I think that's it. We'll see if anybody has questions, feel free to pop them in the Q&A, and we will go ahead to our final speaker for the evening, Kate, and we're going to do a little tech switch here.
Thank you.
Okay. And we have to screen share. I think this is it, right? Or maybe this is it. Good question. Hello? Exit this. Okay.
And yeah, try that one.
Oh, share. Wait, I'm pressing the wrong button. Okay. And then
You'll want to go forward. Forward is that way. Oh, does that not work?
oh wait, maybe I have to click on it. Sorry. Oops, not a right click. Okay. Okay, great.
And let's get rid of that thing as well. Hide. There we go.
Is it working?
I think so.
Cool.
Okay, yes. Oh, that's a good
Hi.
idea.
Thank
Wait,
you.
how do I press the
Press
little
that one.
thing?
Yeah,
Okay,
exactly.
cool.
Good, good.
Okay.
Thank you.
Wait, did we unmute this? Maybe we did.
I think you're unmuted.
Okay.
Yeah.
Okay, cool. Hi, everyone. My name is Kate Chevelle, and this summer I worked with Dr. Lindsay King at the University of Texas, Dallas. And today I'll be talking about our quest to understand the most massive objects in the universe. So this presentation is divided into two parts. First, I'll talk about the most massive objects in the universe, known as galaxy clusters. We'll talk about what they are and how they relate to dark matter. And then I'll talk about how we use simulations to study galaxy clusters. I'll talk about what cosmological simulations even are and how I've used them in my own research. So first, I want you to think about everything you've ever seen on Earth, all the people you've ever met, all the places you've ever been, and then think about all the stuff in our own universe, all the gas, dust, planets, and matter, and then think about every galaxy in our universe. So all of that stuff is only 5% of the total matter in our universe. The other 95% is dark energy and dark matter, but for this talk specifically, I'll be focusing on dark matter. So as I mentioned, galaxy clusters are the largest gravitationally bound structures in our universe, and they're created when individual galaxies merge together. They have three main components: galaxies, gas clouds, and dark matter. And so their dark matter is in around the individual galaxy, and when these objects mesh together, they create a larger dark matter halo around the cluster. And so this is a really good way that we can study dark matter. Galaxy clusters become a very helpful probe for us. And here you can see a visualization of the dark matter. It's that purplish haze in the image around the galaxy cluster. So we know a couple things about dark matter. First, we know it exists. It was discovered first in the 1930s by Fritz Zwicky, and then again in the 1970s by Vera Reuben. And both scientists found that objects in galaxy clusters and galaxies were moving way too fast for these structures to remain bound. And that meant there had to be some unseen matter. And so that leads me to this next point. It doesn't emit light. So we can't see it. It doesn't interact with electromagnetic forces. It also has gravity. And we know this because it encourages objects like galaxy clusters to come together. And this is a visualization of objects in the universe clumping together. You can see it starts at some point and runs to the present day, which is z = 0. And you can see it forms kind of like a spider web-like structure. And that follows a type of formation we know as hierarchical structure formation. And this says that smaller objects will coalesce together to make larger ones. And this means that dark matter particles are cold. So cold, warm, and hot relate to the different types of movement dark matter particles can have. And here I have another image from a simulation. You can see an early and a late stage of the universe. So if you had cold dark matter, objects would clump together more, kind of like ice. And then you would have a lot of big objects in a late stage of the universe. If you had warmer dark matter, kind of like water, you'd have less massive structures. And so you can see that here too. There are not as many massive structures between the cold and the warm dark matter universes. And if you had hot dark matter, you'd have very, very few large structures, very similar to steam, very diffuse. And you can definitely see a stark difference between all three different types of dark matter. So I've put up a bunch of images of simulations, but now I want to talk about what they specifically are. So simulations are 3D models of nature or the universe, and they can take days to weeks to months to run. And they're run on machines with intense computing power, so not my own personal laptop. And they basically allow us to study things that would otherwise be very, very difficult to study, like objects in our distant universe. And the goal in simulations is not to reproduce an exact image. Rather, it's to produce something that's kind of proportional to what we see. And this is a good example of that. We have a picture of the Hubble Space Telescope, and then we have a picture from a simulation. And you can see how the images are similar, but not exactly the same. So in my research, I used a simulation called Illustrious TNG. And this was a large 3D simulation of evolving galaxy clusters over time. And it has four main objects. It has gas, it has dark matter, stars, and black holes. And so my research goals were basically to see how galaxy clusters evolve over time. And so I asked a bunch of questions. I asked, how many are there and how massive are they? How do they form? What do they look like in space? And how does the simulation match real world observations? And for this presentation, I'll focus on questions 2 and 4. How do they form and does the simulation match real world observations? So when trying to answer the question, how do they form? We studied their masses over time, creating a plot of their mass history. And you can see that here. And the masses seem to steadily increase over time. And this follows the logic of hierarchical structure formation, with smaller objects coming together to form these bigger objects. And if you were to track them, you would see that they start at a really low mass, eventually getting to a very big mass. And then we can try to confirm this through visualizations. And so we looked at a specific object called Halo 0, a massive galaxy cluster, at a bunch of different points in time. And so you can see that as time continues, the shape changes. And you can see in the first image at the very far left, something enters the bottom of the image and it seems to pass through an exit. And you can also see that the density of the object changes, with the darker regions being less dense and the wider, brighter regions being more dense. And you can see that white spot in the center of the image increases over time. And this indicates potentially a merger. So now to answer how do these simulations even match real world observations, we took the same galaxy cluster, Halo 0, and compared it to an object in nature called JKCS 041. And we saw a lot of similarities between these two systems. First, they're both located around the same point in time, both at a point in the early universe. They're both still in the process of forming, and they will both become massive clusters by the end of their lifetime. Specifically in Halo 0's case, because it is a simulation and we have access to its whole life, we can see that it does become one of the most massive objects in the simulation. And at the last moment of the simulation, it is the most massive object, period. Some of the differences between these objects are that Halo 0 is much less massive than JKCS. And this is basically just because of the limited volume of the simulation. If we had a bigger simulation, we'd probably have a better match between their masses. And we also did another visual analysis. We created a visualization of Halo 0 as potentially seen through the new James Webb Space Telescope. And then we compared that to an existing image of JKCS through the Hubble Space Telescope. And you can see, obviously the images are different, but they both contain a central bright spot and have a lot of bright spots around them. So the main takeaways, or the things I want you to remember: galaxy clusters are the largest structures in the universe and a helpful probe to understand dark matter. We know 3 things about dark matter. It exists, it doesn't emit any light, and it has gravity. Large-scale cosmological simulation allow us to model nature, leading us to better understand it. And illustrious TNG simulation shows us how masses follow hierarchical structure formation to form larger objects. And these simulated objects are comparable to things we can see in real life. Thank you.
All right, questions. We do have one in the Zoom room. Maybe we'll start with that one while people think about other questions they might have. The question from Zoom is, what excited you about dark matter?
Okay, so I think what excites me most about dark matter is a couple of years ago, there was this theory that came out. It's this cosmic particle, and it was related to string theory, which, say what you will about string theory, it's a very complicated science. But basically it was this idea that dark matter particles could potentially be particles that are part of a different dimension and they're vibrating at a different frequency than all of us. And I just thought that was really cool. We don't really know what it is, so that could still be a possibility. But yeah, I thought that was a very cool thing about dark matter. And that drew me to try to do something related to it.
Awesome.
Yes, Celia.
Thank you, Kate. That was awesome. I want to, like, before I ask my question, I just want to say, like, that was one of the best analogies I've ever heard about, like, cold, warm, and
Oh, thank
hot
you.
matter. And, like, I think, like, I understand, like, dark matter better because of you. Thank you. I wanted to ask a question about the plot you had about tracing 4 different galaxy clusters.
Sure.
So I'm interested with the few of them that they took pretty sharp dips along the way. Is that related to a real kind of, what is the word I'm looking for, like an event happening, or is that something in the simulation that it's not real?
Yeah, so both. So basically, there's an issue in Illustrious, and it's a very complicated simulation. And one of the issues is the naming system. And sometimes when objects merge, the simulation has a hard time identifying what is what. And so basically these dips sometimes come up as the ID shifting, or sometimes they're actually indicative of a merger. So sometimes when objects merge, the mass is taken from an object and put into another one, so you would see a dip in its mass. So we have a hard time distinguishing between these two. So oftentimes we go to these visualizations to check, or we use like other kind of parameters or objects within the simulation, like velocity, like how fast an object is moving. Are they moving just as fast as each other? The coordinates, are they even located near each other in space? Things like that. But yeah, this is a very difficult thing because sometimes you think, oh, we're seeing a merger because of this big dip, and then it's actually no, it's just having a hard time categorizing these objects that are crossing each other.
Oh, interesting.
Yeah.
We do have a question on Zoom, which is, do you know how much more volume you would need in your simulation to make Halo 0 comparable to the natural, you sort of said that the nature in the simulation, one of the reasons they might not match is because you don't have a big enough volume in the simulation.
Yeah, I'm not sure like the exact number. It's interesting because Illustrious TNG actually has 3 volumes, and this is the biggest one.
Okay.
So like the way that there's a disparity between those 2 volumes already, like I can't even imagine what it would be like if you took the first volume, like how much tinier it would be. But yeah, I'm not sure the exact proportions. Yeah.
We need a really big supercomputer for that.
Yes.
Cool.
Do I just leave it or?
Yeah.
Okay,
you
thank
can
you.
leave it. Watch the core. All right. This is going to be the last call for questions on Zoom. I see lots of thank yous, very interesting, great job from Zoom land. We have about 40 people out in Zoom world who have been watching, just FYI. And if there's any more last questions, feel free for any of the interns. And I just like to thank you all for being super awesome. I want to tell you how difficult it is, by the way, to summarize your 10 weeks of research into an 8-minute talk for the public. That is, supposed to be expecting 0 background information. Yeah.
No, I understand. You said for the public, and that's being very ungenerous.
Yes.
Many of us don't understand.
Yes. Yes. Well, that's what we're trying to make it so that you can come in with 0 sort of background information and get something out of what everybody worked on this summer. And it is very, very difficult. So I want to thank you all for doing that Herculean task. And then also just for being awesome all summer. You really made it a fantastic summer. So I'm gonna start crying. And yes, there's lots of great jobs on the Zoom. I don't see any more questions though. So thank you all for coming. We will hang out for a couple more minutes if anybody wants to chit chat, and then we're going to head up to open night. So where you can hear more if you want. So thank you all.
No rest for the weary at the MMA.
Thank you so much, Will, and thank you to everybody out there on the Zoom. We will be posting this recording on our YouTube channel. Thank you all. Good night.
That was really impressive.